Hello, everyone, and welcome to today's webinar brought to you by the MIPI Alliance called How to Get Started with the MIPI I3C interface. Today, we'll learn how to get started with the MIPI I3C interface, the modern successor to I2C and SPI, and see it in action. We have three highly knowledgeable presenters joining us. So first, I'd like to welcome Ayuel Teferi. He's the Senior Hardware Design Engineer at ST Microelectronics. Ayuel, how are you doing?
Hello, Brian. Hello, everyone. Thank you very much for joining us in this I3C overview.
Excellent to have you here. I look forward to your presentation. Ayuel is chair of the MIPI I3C working group. He brings deep experience in MEMS sensor interfaces and leads the ongoing evolution of the I3C bus specification. And next, we have Jonathan Georgino, founder and CTO of Binyo LLC. Jonathan, welcome.
Thank you so much. It's a pleasure to be here.
Awesome. Pleasure to have you here. Jonathan is co-vice chair of the MIPI I3C working group. He's a hands-on hardware engineer who's brought numerous tools and boards to market and now leads efforts to help designers and engineers adopt I3C in real-world designs. And finally, we have Kai Gosner, a passionate community evangelist for the I3C bus. Kai, welcome.
Yeah, thanks for inviting and joining.
Kai is the creator of the I3C Blaster, which is an open source USB to I3C bridge based on the Raspberry Pi Pico. So he'll take us through the practical side of getting hands-on with I3C today. Now let's have a look at our agenda with our experts lined up and ready to bring you the insight story. Firstly, Ayuel will start with a MIPI I3C overview, explaining the MIPI Alliance, I3C fundamentals, where the interface fits in mobile, IoT, and automotive, and its key advantages over I2C and SPI. Jonathan will then show how to get started with I3C, covering hardware examples, developer resources, and current adoption. And finally, Kai will present a hands-on demo using the I3C Blaster, a learning and debugging tool built on an RP2040. And while our speakers present, I see people from all around the world joining us as usual in the comments. Please post your questions in the comments. We'll address as many as possible in the Q&A session after the presentations. So we'll start with Ayuel. Could you give us your overview of MIPI I3C?
Thank you very much, Brian. I will be doing an MIPI I3C overview and introduction. Let me start with MIPI Alliance, introduction to MIPI Alliance. MIPI Alliance is an collaborative global organization that is started as a development of specifications for mobile and mobile-influenced devices and markets. Later, it has also expanded its scope outside of the mobile and mobile-influenced into IoT, PC, personal computers, automotive, and industrial applications as well. As you can see here on the right, that the MIPI is composed of more than 375 member companies, of which these companies are made up of semiconductor companies, IP vendors, software companies, test equipment manufacturers, automotive OEMs, or Tier 1 providers, providing all their insight and industry experience into developing the most recognized MIPI specifications, the ones that are shown on top there, like the CSI, DSI, I3C, FI, and the other, which are most commonly used MIPI I3C specifications. Going to the MIPI I3C interface, MIPI I3C, as I said earlier, it started with consumer, mobile, and wearable markets. That's why you can find MIPI I3C in most of the sensor devices and sensor markets. But it wasn't only limited to that one. In line with the vision of MIPI, it has also expanded some of the use cases into IoT, industrial, and automotive applications. It has tried to achieve these fast-growing sensor markets by being CMOS I/O compatible, low wire count, and high-speed communication that is aimed at replacing and improving the traditionally existing I2C, SPI and UART-based communications, but at the same time trying to achieve a lower complexity. As you can see on this slide, on the left side of the presentation, you can see that on top there is an I2C-based communication and an I2C-based controller. Then there is also an SPI-based communication and a UART-based connection to the system on chip. And from all of this, you can see that I2C has a two-wire communication, which is an advantage, and why I3C is also based on top of I2C. But the drawback is that it has been limited by speed, and it requires a dedicated interrupt lines to come from the devices to the system controller or system on chip. When we come to SPI, SPI has a faster communication, but it is a highly GPIO and routing intensive communication protocol, especially when we try to, every time we add a new device, then we should also have one dedicated GPIO pin for the chip select. On top of this one, we also have multiple interrupt lines coming to the system on chip, which means that the controller or the system on chip will have to have an SPI-based hardware driver plus controller, an I2C-based controller, a UART-based controller, and on top of this, there should also be an interrupt controller that is running. And all of these are firmwares and latency contributors, including also power consumption on the system on chip while trying to run all these operations in parallel. When we move to I3C, I3C tried to unify and take the best features of the existing protocols by taking two-wire communication from I2C and adopting a push-pull type of signaling from SPI to improve the data throughput and communication frequency. By doing this and by using an open drain-based arbitration mechanism to send an inbound interrupt, I3C has effectively aimed and succeeded in reducing the wire count and complexity of system design by, as shown on the right side of the presentation. Here, on the next one, you can see that I3C has two different versions of a specification. The first version of the first one, you can see that there is an I3C specification, which is a member-only specification that was first released in 2016, and it added a new set of features in version 1.1 and 1.1.1, the revised edition, and version 1.2 was a revision and a formal structuring of the specification. Then, as a subset of I3C specification, but that is freely available for the general public and general use, there is an I3C Basic specification, which has a rich subset of I3C features available, with some features that are reserved for MIPI members only. And it, as you can see, that it's always released as a subset and as part of an I3C specification. Here, the two flavors, to be able to use the full I3C features, companies have to become members, while to use I3C Basic is freely available to use. When we come to an I3C bus configuration, as you can see here, I3C can support, and the first part is that it's backward I2C compliant because it's built on an I2C device. So you will see that there is an I2C device here. Then there are I3C target devices that are devices that respond to controller requests from master or I2C controller devices. On I3C, there is always there is a special improvement in multi-master system or multi-controller system where the I3C primary controller is only one. So in I3C, it's allowed to have only one I3C controller, primary controller, and other controllers could come up as a target device and later request to become a controller. And when they are granted, they could take ownership of the bus. This allows to avoid the arbitration of controllers on the bus and for a better bus management and a better handoff procedure from one controller to another controller. By doing this, I3C also ensures that there will be no overlapping and also there is only one active controller at a time. The other devices that you see on this bus are the I3C bridging and routing devices, where a routing device could be used to send an I3C communication down to a downstream I3C bus or an I2C bus downstream, while a bridging device could also be used to receive an I3C command using the I3C bus and to send a communication to downstream devices that could be other protocols like SPI, I2C, or other bridged networks. Next to this, we have the MIPI I3C electrical bus drive. Speaking about this, I3C, as I explained earlier, is built on top of I2C, which means that you will see some of the common features that are present in I2C, like the start condition, the stop condition, repeated start condition, and the basic data signaling, that is the data changes only when clock is low, and data is sampled on the rising edge or when clock is high. So these are the basic communications that are used by I3C, where it's built on top of I2C. But in contradiction to I2C, or as an improvement for on top of I2C, I3C uses a push-pull type signaling for clock to make sure that there is a faster clock switching. And it also uses a push-pull data transmission during a data transfer, while it uses an open drain type signaling whenever it is necessary, but in a few limited use cases where the controller wants to have an arbitration on the bus. I3C allows multi-controller system, as explained earlier, and on I3C there is a managed and controlled handover of bus ownership from one controller to another controller. I3C overcomes limitations of previous protocols, especially I2C, by allowing dynamic addressing of devices. It has also an extended operating voltage range of 1.2 up to 3.3 volt, but the features, most of the features are the maximum clock frequencies that is achieved by using the push-pull clock, that is 12.5 megahertz in a single data rate, while there are higher data rates that are provided, and I3C could reach and support up to 100 megabit per second of communication. Looking on the basic commands that are the ones that are built on top of the I2C, on top you can see that there is a private read-write communication or normal data read-write communication. And from here you can see that there, in all these communications, there is a broadcast address that is reserved for all I3C devices to be acknowledged. But whenever this broadcast address is followed by repeated start and then a dynamic address or a device address follows, then it will be a private read and write communication. Then I3C has added a set of common command codes that are mutually recognizable by all devices on the bus. And in this case, whenever the broadcast command is followed by a data instead of repeated start, then that data will be interpreted as a command code, and it will be understood by all devices on the bus, or I3C supporting devices on the bus. I3C, like I said earlier, it could reach up to 100 megabit per second, and this is achieved by allowing I3C to have multi-lane communications. Whenever the data throughput or higher data throughput is required, then we could increase the number of data lanes of I3C to 2 wires or 4-wire communication, and by doing this, we double or quadruple the data throughput. But not only this one, I3C also allows a data where dual data rate or double data rate communication is supported. In this case, the data changes on both clock edges, that is on falling edge and rising edge of the clock. And by doing this, it achieves a higher data throughput for a provided frequency. That means on a basic 12.5 megahertz clock, we can have 25 megabit per second of raw data and an effective data rate of up to 22 megabit per second. Or in case of an I3C TSP, ternary coding protocol, where clock and data are used to transfer data, we could achieve up to 33 megabit per second. On top of this, we also have a bulk transport mode that is based on top of the DDR mode, but that allows data packing to make sure that the effective data throughput is also further improved on top of the DDR communication. Moving to the next one, I3C achieves a higher data throughput. Here, there is a comparison with I2C where it's built upon. So you can see that using the single data line, that is one clock and one data line, it's possible to achieve up to 11.1 megabit per second. That is an effective data rate. And by increasing the number of lines to dual lane or quad lane, we could double or quadruple the data throughput. On the other hand, when using the other signaling modes, higher data rates, then we could also have 20 megabit per second, 40 and 80. And using the encoding meters that are provided, we could also reach up to 100 megabit per second. This is not only assisting on high data throughput, but the faster communication with devices on the bus allows the controller to finish the data transfer or to finish operations and stay in low power mode or inactive, only needs to wake up when it needs to gather data, and it could gather the data in a shorter and faster way, and then it could go back to power down mode, saving energy and saving time also and latency. I3C, like I said earlier, there is a new version 1.2 that has been released in the past year, and this one does not have any major changes or new features added, but it has organized the specification for an easy-to-use organization where the required elements are separated from optional features, and all required sections are explained in detail on the first part of the specification for anyone that wants to see the minimal subset, and optional features are collected as a feature-based specification and a new reorganization. From here, you can see that I3C is not only an I3C protocol or communication protocol, but it has also a set of supporting protocols that are developed by other MIPI work groups. One of the first one is the MIPI host controller interface that is used and that is developed to make sure that host controller or controller manufacturers are able to use and standardize the MIPI, the controller hardware, and how to communicate and retrieve data from target devices, or how to manage the I3C bus. There is a MIPI I3C TCRI, transfer command response instruction or specification, where an I3C command can be sent using another type of bus. This way, a near end or another I3C controller can send an I3C command to another device, and that one will decode this one. So this is also for mapping I3C specification on top of other protocols or other buses. And there is also an ongoing and continuously updated DISCO protocol or discovery protocol of I3C, where devices on the bus are dynamically discovered and updated on the host controller interface. Here we do have a few further information and for supporting materials also. MIPI I3C work group provides a frequently asked question, app notes, conformance test suits, and also there are a few webinars that are presented, and we are also presenting at the Embedded World in North America and also the one in Germany. So please join us, and here you can find a list of links where you can find also supporting documents for I3C development. Thank you.
Well, thanks for that. Well, it's nice to hear I can say I3C because I've been battling with I3C. That was very enlightening. I would now go to Jonathan after Ewell has given us a great overview of the technology. Let's bring Jonathan up here. Jonathan, up on stage.
Hello.
There, thank you. So, Jonathan, how would someone take a first practical step with the bus?
Yeah, that's a great question, Brian. Thanks so much for having me here. So the first steps to actually getting up and running with I3C are to look at where and how it's currently being used. Then we can take a look at what devices are available already on the open market based on these use cases. Then we can identify which of those might be interesting based on different points or capabilities that they have or that they implement in the I3C spec. And then we'll also highlight a few supporting resources that go along with these devices. So with that should prepare everybody attending this webinar to be ready for Kai's hands-on part of this demo. So let's go ahead and dive into this. So where is MIPI I3C being used already today? It's actually widely adopted in several market segments. There's three here that I would like to highlight. The first of which is the use case in DDR5 memory DIMMs. So in this case, MIPI I3C protocol is used for the sideband management bus communications. Specifically, it's used to monitor the temperature sensors on the DIMMs, so that way the memory can be properly managed. And so as computers want to push memory utilization to be more and more aggressive, monitoring that temperature with a tight closed loop becomes more and more important. Previously, this use case was using I2C and SM bus, and the temperature sensors on each DIMM needed to be sampled. Now, if you think about enterprise server equipment where there's many DIMMs on a server backplane, the slow speeds of I2C can become a limiting factor at how fast the temperature data can be aggregated and if the processor can adjust memory utilization. So by adjusting this use case, upgrading this bus to I3C and gaining the advanced speeds and bandwidth throughput and some other features offered by I3C, memory can now be driven much more aggressively, knowing that the control loop on getting that temperature data will be closed faster. There's no reduced risk of thermal events by not being able to throttle back memory utilization as temperatures increase. So that's probably one of the most entrenched market use cases already. The next one I want to talk about is similar in the sense that I3C is being used as the sideband management bus for communications on SSDs. Right now, this is in high-end enterprise SSDs. This has been adopted by the PCI SIG as the official sideband communication layer for PCIe. And in this case, I3C is used as the transport layer for a protocol called NVMe management interface and MCT protocols. So thanks to I3C's backwards compatibility, again, this was a use case previously served by I2C and SM bus. But with I3C being adopted here, the throughput increases, and it makes for a smooth transition from the current implementation to the next generation, where these devices are actually starting up in the legacy SM bus mode, and only once the controller attempts to upgrade the bus into I3C mode of operation, if the supporting SSD can handle that, it upgrades the communication and makes for a smooth, seamless transition to a higher performance mode. And so the last use case that I'd like to immediately identify as being quite popular, and this feeds into what Yul had mentioned in his part of the presentation, is that it's in a lot of consumer devices, especially now as we see a lot of augmented reality, virtual reality, and AI-enabled wearables. And so this is becoming more and more popular here, and it's based on some of the boxes or requirements that I3C can help fulfill that are relevant to these product spaces. So specifically for wearables and augmented reality, virtual reality devices, the pin-friendly, compact implementation of I3C really helps achieve the consumer form factors needed for these products to be successful. So there's just SCL, SDA, 2 signals. There's not a need to fan out additional GPIOs and signals to all of the sensor devices. There's no need for interrupt lines, dedicated reset lines, because all that is handled by the common command codes within the I3C specification. I3C also is an optimal choice for battery-powered devices. Because most of the I3C communication takes place in push-pull mode, it's much more power efficient compared to trying to send the same amount of information over I2C, where power is being burned through the pull-up resistors each time you send a low value. And of course, it goes without mentioning, I3C, SDR data rate is sending data up to 12.5 megabit per second clock rate. This reduces the amount of time when sampling different sensors to get their data. And so you get tighter data for more accurate sensor fusion applications. And so this is what's really driving the I3C adoption into these 3 different use cases. There's many others that are also there, but highlighting these are, I think, a great starting point to see, what is I3C already being used in the market today. Looking ahead, there's also some use cases for where it's going to be showing up more and more over the coming months and years, actually. And 2 of the use cases here that I'd like to highlight are on the low power image sensors and IO bridging. So in the case of low power image sensors, this is a quite exciting activity where the I3C bus isn't just being used as a sideband communication bus, like controlling the camera configuration alongside a MIPI CSI, but is actually being used as the conduit for image sensor data. And so that has some interesting effects where we're able to get even lower power images where we can turn off the CSI interface and just use a low power bus like I3C to send that image data on a battery powered device. It also enables lower power general purpose microcontrollers that otherwise wouldn't be able to support communication with image sensors. Low power devices that don't necessarily have CSI or have a parallel bus for a camera can now get image sensor data into them over the I3C bus. There's several MIPI members that are working on very novel solutions in this space. I'd encourage you to look at some of the demos and collateral that they've released to see exactly how they're using I3C in these implementations. The other topic I'd like to show that's coming up as an interesting use case for I3C is in IO bridging. And so this is effectively a use case where we're aggregating I2C, SPI, UART, and GPIOs and other protocols and encapsulating them over an I3C bus. This has the benefit for very constrained spaces where you want to pass a lot of different protocols, but just through 2 conductors. And so if you can think of a use case where on a laptop screen or any device with a folding screen, effectively where you're passing electrical wiring through a hinge, being able to condense all of those signals down to just 2 conductors really does a lot in making this electromechanical connection much more robust and featureful. So this is another working group within the MIPI Alliance that's working on creating a standard to specify and standardize the communication of encapsulating these protocols over I3C. So that's where MIPI I3C is headed next. But now that we've covered these use cases, let's talk about what's available today. So there's an ample selection of I3C target devices. Based on the use cases we had just covered, you can see that there's going to be temperature sensors, MEMS sensors, inertial measurement, biosensors. Those are all available. Many of them are available on dev kits as well for the, on DigiKey Mouser. All of the usual catalog distributors are carrying them. There's a different implementation for all sorts of things. As a great starting point, we just like to highlight some superlatives for different features, because many of the I3C features are actually optional to implement. And so as a result, you want to select a sensor to start with based on the features of I3C that you're most interested in exploring. And so this slide shows some interesting starting points depending on the types of activities you would like to do with I3C. And I would just like to mention, as you all had pointed out, there's been I3C v1.0, v1.1.1, and v1.2 all released. As a result, there's some different capabilities of the devices currently available on the market. They're all compatible with each other. However, just to set expectations, there can be some different behaviors. So you will want to pay attention to which version of the I3C specification the targets have implemented. So we talked about targets now. Let's talk about controllers. Historically speaking, this was a little bit harder to get up and running with. And as a result, I think we're quite motivating for Kai and his creation of the I3C Blaster that he's going to talk about. I'll just mention that for the longest time, you had to find a dev board that supported I3C controller. This slide shows that there are quite a few available now. However, I would like to just skip right over this and get to Kai's use case, because what he's going to show you is an even easier way to get up and running with I3C than trying to get a dev board up and running. So yeah, that's kind of a quick survey of the physical devices that are available to get started with. The last thing I'll mention here before I turn it over are the other helpful resources beyond what the MIPI Alliance has produced as collateral and supporting materials. A number of vendors that have been implementing this have created a lot of marketing collateral, including videos, podcasts, data sheets, white notes. They're all here available on the vendors' websites, and I highly encourage you to also leverage those as you begin your journey in I3C. So with that, I'd like to go ahead and cue everything up for the main event here with Kai and his I3C Blaster. So thank you, Brian, for having me be a part of this.
Thank you, Jonathan, for taking us through that. And finally, Kai, I'm looking forward to this for some real hands-on experience. Kai, show us your I3C Blaster and what it can do.
Yeah, thanks. So I was invited to show and demonstrate a few tools I created around I3C to enable an easy kickstart to I3C on low budget. It's maybe not the high-level professional tools, but it will enable you certainly to make the first few steps. So I was interested to start getting a deep understanding of I3C, and was really blasted away by the huge amount of pages the specification has compared to I2C. So the way I learn is typically not from only reading a long specification, but being able to interact and to see and do things and then correlate that with the specification. So instead of taking something off the shelf, I started a low-level implementation of I3C. You could say it is bit banging, but it's actually hardware-assisted bit banging using an RP2040 PU module and programmed the C software around it to be able to create I3C transfers. And that is one thing. Later, I will show some other tools also. But most people will basically have RP2040s lying around on the shelf, and you can do a lot of things with them. So that enables you, just by adding 2 resistors, to have an I3C master available or I3C controller available that you can use. And later I will also show it. So what can it do? On the right side, you see a lot of commands, and I'm not walking you through detail through that one. On the project page, you can read it. But I think it is a close to 100% implementation of the I3C Basic specification, supporting SDR mode transfers, HDR, DDR transfers. And on top of that, it supports also I2C operations. So you can do classical operation on I2C, where also the SCL line is operated in open drain mode. So I3C Blaster has several usage schemes. No one showed here. So basically here in the middle, you have the I3C Blaster, which is your RB2040 with the 2 pull-up resistors. You connect the USB port to your PC to be able to control it. And on the right side, you connect either one or multiple I3C or I2C devices, or even a mix of them. So the first usage mode, which is really nice in the beginning or to debug something, is interactive usage. So you can type in a kind of interactive shell console window. You can type commands, see the reaction back in human readable format. The second usage is talking using Python scripts to your I3C devices, so you can interactively use it. And the third use case is, it is basically a software library which you can directly integrate in your own projects. So I'm always a fan of also explicitly showing some limitations of the tool. It is not let's say a commercial grade, extremely high quality tool, but I think I made it quite accurate to the specification. However, RB2040, at least those standard boards, support only 3.3 volt I/O levels. Many I3C devices operate on lower voltages, like 1.8 volt, for example. So you would need to add external level translations. As part of the project, I also made a level translator board, which could be used, and you could build it yourself or use other level translators. Another thing is, because I'm using a USB with a CDC or virtual UART, that limits the latency a lot. So there's a lot of processing overhead. So to make it interact with less latency or faster, you would actually need to implement a proper custom USB protocol on top of it. So it is a little bit slower than an actual I3C master because there are some phases where there is additional software overhead or turnaround which needs to be handled. And also passive pull-up resistors are used here, while that would, for an actual I3C master, look actually a bit different, especially on the SCL line. Signal integrity, I think that's not necessarily only a thing here, but I noticed, especially after enabling DDR support, if you just use your classical Arduino Dupont kind of wires, it can be difficult to get the signal integrity right. So there are options to set the drive strength, but it's in general a good idea to look with a scope also what you are doing. And here you're seeing on the right side, you're seeing two measurements done with a proper differential probe setup. So the top one is done with long wires, and you see lots of overswing, and that can even lead to wrong detection on a target side and wrong reactions. And the lower one is actually one where I tuned the drive strength settings and also got rid of the long wires and hooked it up directly by plugging it into the pin header. So another thing I made, because it's nice to have a tool with that you can interact with your devices, is I3C decoder plugins for two popular logic analyzers. One of them is the SALI analyzer. The other one is SIGROC Pulse View, but also the derivative of it, which is DS-Logic DS-View. And you can use it to decode I3C transfer. That helps specifically because I3C is different, and especially the acknowledgement phase is utilized different compared to I2C, and it can have, based on context, also a very different meaning. And especially when you start looking into DDR transfers, it will get difficult really to understand and interpret the transaction without such a decoder. So let me make a short demo and get to the lab bench and share my screen. So what you see on the screen here on the bottom side, is basically logic analyzer view. You see SDA and SCL line, and also the decoder here to be able to follow a bit. So I will demonstrate first the use case 1, which is that you can connect with PuTTY just to a serial port, here COM4. And then this is interactive use now. So you have I3C Blaster here, and let me enlarge that a bit, and you can type commands. And you can, let's start with the help command. You can enter help, but you can also do help and then I2C TWOC, for example. Then it will show you also help for that specific command. We can also interact, of course, and let me maybe start with a reset dynamic address assignment, and then you immediately see here in the logic analyzer first I3C transaction. And one thing, if you're new to I3C, actually I used a hardware controller in the beginning. I was really confused about these short needle pulses here. I thought something is wrong. I programmed the software wrong, but actually the purpose of that is they are in length below 50 nanoseconds. And the reason is that I2C slaves have typically a filter integrated to filter away short pulses to have a better signal integrity. And that is used in I3C to isolate I2C devices from seeing I3C transactions. That is why you see the short needle pulses here. You mostly see there are use cases where it can be SDR mode and push-pull mode continuously, but typically a transfer is started with open drain mode, and which is slower. And you see that here. There is the broadcast address is addressed 7E, and then there is an SDR mode transfer with 12.5 megahertz, which is in push-pull mode, and you have the ability then basically to transfer data quickly. Another feature is you can scan for addresses, and you see here the default address of the device that I'm using, which is 0x68. It's a 7-bit address, and also the broadcast address of 7E where it responds to. Just to show, you can also do dynamic address assignment, and you can basically, this command will basically now assign address 30 hex to the connected I3C target. And what you see here is then basically the decoding of the sequence of the enter dynamic address assignment, which is done. There is information read from the device, and at the end, that part is actually the actual address assignment. And you see also the read data back here. And yeah, and that way you can interact with the devices. You have equivalents also to do I3C transfers, I3C DDR transfers. It will take care of also generating special bus conditions like target reset, entering HDR, DDR mode, and exiting it. So that is all part of it. This is use case 1. Second use case I want to show is basically a short snippet of Python code. So what you see here is a code which does a 3D, which shows a 3D model, and I read out an I3C MEMS device and show basically live the orientation of the module. So I can also show that and quickly start that. Yeah, that happens when you don't close the UART connection. So you see here at the bottom, you see the retransfers. 6 bytes are read, 2 bytes per axis, and then here on top you can basically see when I rotate the module, then also the model rotates, and that is basically just showing one use case. Huh? So let me maybe go to the last slide. So I plan also to further work on that, and one work is right now the RP2040 is supported. I will also port it to the RP2530, and that helps a bit in having a faster PO module, among some other improvements like being able to support also smaller I/O voltages. Once there will be ternary mode targets, I might also look into enabling those. Another thing is also implementing a custom USB interface to get the interaction with the device done with less latency, and also implement PC-side C interface for integration into C environments and calling it from C rather than only from Python. So that's all I wanted to show. Thanks a lot.
Thank you very much, Kai. That was very interesting. Time for the Q&A. We've got a lot of people from all around the world asking questions, so I'll bring everyone up. If you don't mind, I'd like to start with that last slide that you put there, talking about a ternary mode. What would the benefit of that be?
The benefit is that it steps up the transfer speed of your device, so you can transfer data faster while still only using and utilizing 2 data lines.
Okay, great. I've got a question here from Fayez. If I'm understanding the question correctly, I think Fayez is asking, when the power is first applied, that's the cold power on, does the I3C target immediately send a hot join request to the controller, or does it only send a request after it notices bus activity on SDA and SCL?
Maybe I could answer this one. In I3C, we do have 2 different types of hot joining. One is a passive hot join, where the I3C device that is connected to the bus makes sure that the bus is an I3C bus by seeing the broadcast address that is reserved for I3C. And only after recognizing this, that the device could send a hot join request. This is whenever we try to use I3C for a mixed bus use case, where the devices could be, as we all said, that they could be backward compatible with I2C, or devices could start as I2C and could switch to an I3C mode. So to avoid blocking the bus and also to avoid I2C controllers from being blocked because they do not expect a hot join request, we have this passive hot join. Then whenever we have a pure I3C bus, that is all devices, including the controller and all targets that are on the bus are I3C only devices, then we do have an active hot join request. In this case, the controller is able to handle a hot join request, and based on this request, the controller may accept it and then assign a dynamic address, or if it's not ready to accept a hot join request, it could simply knock the hot join request from the targets and send a broadcast command, because I3C have built-in commands that could be sent to all devices. It could send a desec or disable hot join command, which is understood by all devices by sending it in broadcast mode. It's understood by all I3C capable devices, and when the controller sends this one, it could block devices from sending a hot join request. So we do have 2 modes to allow backward compliance and also to be usable in 2 different buses, but we also allow the I3C controller to manage the bus and manage what type of requests it wants to receive by using the standardized command codes.
Great, thank you, Eyo. Got a bit of contention here around Wolfgang saying that bus clock stretching is not supported, but Marcio asks if the I3C clock line is always in push-pull. how does it handle I2C devices on the bus that perform clock stretching? So if someone could clarify that.
It is basically not supported. When you have mixed mode I3C, I2C, the I2C devices should not or are not allowed to clock stretch.
Okay.
Yeah, we do have
question
a
from me.
system. Just to add on this, because there seems to be a few questions about I2C and I3C use case. So whenever we try to move forward and improve something, we always need to give up some of the features that are in I2C. And one of these features is the clock stretching. And usually, even when the target devices are stuck in stretching mode, even the bus and the system cannot be recovered. So to make sure that I3C is in full control of the controller or the active controller of the bus, the clock is always driven by the controller and in push-pull mode for higher frequency. On top of this, when we try to mix I2C and I3C devices, we do have a few restrictions. One of them is the I2C devices are always required to have a 50 nanosecond spike filter because I2C devices are working at lower frequency and higher frequency communication of I3C could disrupt with the communication or with the internal finite state machine of I2C devices. So to make sure that these devices are not impacted, we force the I3C devices or to have, as Kai, in fact, brilliantly explained by showing the duty cycling of the clock, where the T high is always limited to be under 50 nanosecond, making it practically invisible for I2C devices to see this. So this one ensures that the I2C devices can be used on an I3C bus in a safe condition, and whenever the communication is with I2C devices, the clock frequency can be reduced. The other is clock stretching and 10-bit addressing are restricted and not allowed on an I3C bus to ensure that this works in a faster and efficient way for the intended I3C communication purposes.
Okay, awesome, thanks. Kai, for you, I've also got a box of tricks here that I can shake around like you did.
More.
You mentioned needing level shifters for use with the Raspberry Pi Pico, which can be a bit cumbersome at times. But if you were starting with a brand new design, what sort of design paradigm would you use to work around I3C?
It depends on the intention, what I would like to do. So if the intention is a similar one, like now, and I would also like to have the ability to introduce faults or to do on purpose something wrong on I3C to test, for example, the response of a device if it's correct. Also, I would still go for a setup with API 2530, for example, the newer variant of the device. However, I think if you have a serious use case where you would like to interact with I3C devices and you're not so much interested in the learning aspects also, then I think it's certainly good to use a microcontroller with integrated I3C. And in the meantime, there are quite a lot available already, like ESP32 has it, and a lot of others too.
Okay. I've seen this question a bit. I'm also curious, why does the SCL line have a pull-up? I thought that wasn't required for I3C.
Yeah, the reason here is that I also wanted to support classical I2C transfers where you can have clock stretching also. So in a situation where you also have I2C devices connected, you also have the ability to do clock stretching basically together with I3C Blaster. It will have a negative impact on the energy consumption at all, but the whole project is not optimized for energy consumption or energy efficiency at all, so it didn't matter.
Awesome. A question from Mark Colmont regarding symmetrical signaling for longer distances. Will there be such a thing, like a bigger machine between front panels and CPU boards?
Yeah, as I said at the beginning of the introduction, I3C was first developed for mobile and mobile influenced applications where we have limited the bus load to be around 50 picofarad of load. which means that the distances and everything is limited to make sure that we achieve also the maximum frequency and higher data throughput for the intended purpose. Now, I3C workgroup is also working to expand this use case to make sure that longer and larger bus loads are supported, which would mean that we may have to recalibrate and readjust the electrical parameters to make it compliant with larger loads, especially whenever there is a delay between transfer controller sending a signal and then the target returning the data. Always the propagation delays and electrical parameters will become very critical, and we're working towards increasing this one, the data throughput, maintaining data throughput and trying to increase the communication distance and also bus load supported by I3C. After saying this, I3C can work at a maximum frequency of 12.5 megahertz. But if you are using a pure bus, for example, you could reduce the communication frequency to a lower. You can reduce the communication frequency and have longer communication, provided that you may have to take care of the electrical signaling and also the ringing and switching noises to be compliant with the electrical parameters and also EMI noises from affecting the data line.
Great, thanks. There was a question earlier from Vyas about hot join, and Piotr also mentions hot joining. He says I3C allows hot join and dynamic addressing. What's the recommended way to prevent a rogue device from joining and getting an address? Do you see an authentication attestation pattern emerging at the bus level?
Well, for hot join and dynamic addressing, you're reading back the information from the device, which identifies what kind of device it is. Like there are also unique ID fields and things like that. So that could be one method of protecting from it. But I'll let maybe also the others answer here.
Yeah, before you answer, there was a similar question from Arun. Any security feature for intrusion planned in I3C? Take those two as a whole.
Okay, maybe I could take this one. Hot joining can be sent by target devices, but it doesn't guarantee the address of a dynamic address assignment, because the assignment of an address is always started and initiated by the controller device on the bus. Having said this, if the controller device would like to assign or has decided or has pre-programmed devices, for example, in secure systems where the number of devices are already limited and given, then any new device that is sending a hot join request is an outsider. So that could be an easy way to identify and not assign a dynamic address to it. The other is that whenever I3C, we also say that it is a multi-controller system. So when one controller gives controller or bus ownership to another device, and this device unknowingly tries to assign also a dynamic address to a new hot joining device, we have a mechanism where whenever there is an active controller passing ownership to another controller device, it has to provide the full bus information, which means that how many devices are there, if there is any change of a dynamic address, if there is a new device that joined the bus, that has to be reported to the new controller. So by doing these check and balances, I3C will make sure that a new device could not join, but could not be assigned a dynamic address. But hot joining is not prohibited, but we could also block devices from sending a hot join by sending the DSEC, like I explained earlier. Whenever the first hot join is sent, then the I3C controller could send a disable hot join request command to disable these requests from coming.
Thanks. There was a question, Kai, whether your Blaster would work with the Seed Studio RP2040. I think you already used that. There we go.
I think that should be the answer. Yes, it does. So with the, I think, I don't know how to pronounce it, but the Xiao or Xiao module is also supported. It doesn't matter which RP2040 you use.
Excellent. And then we spoke about differential for distance. What would the max length of the I3C bus be when DDR is considered?
Okay, this is still based on the electrical parameters, But one advantage of DDR is that if the inter-DDR command is sent at a low in a frequency, and then the DDR communications can happen as a point-to-point system, because once a device is connected, then the mismatch of the clock and data, or the data communications between that specific controller and target. So in this case, DDR could support higher frequency. When it comes to the maximum lengths, again, the bus load and electrical parameters and also the propagation delays are the limiting factors. Other than this, there is no specific or difference between using DDR or SDR as a way of communication other than higher data throughput.
Excellent. Good answer. And we've got other questions on that, so I hope that answered your questions, guys. A couple of comments. Mark Coleman says a Rust library would be great too. And then regarding that signal integrity, Audrey says that cheap jumper wires are not copper but iron. Test your wires with a magnet that may interfere with high-speed I3C applications. And then Ricardo asked if there's a part numbers of commercial devices that use I3C. Thanks, Jonathan Georgino, for answering that in the chat. There's a list of publicly available devices. If you're watching this, you can pause the video there and type in that URL. Let's have a look at what other questions. Here's one. For Kai, are there I3C I/O expanders available like you get for I2C ECF 8574?
I pass over to Jonathan. I'm right now not aware.
Yeah, as of right now, I'm also not aware of one existing on the public market. However, mentioned on the slide that there's the 8-bit MCU that's programmable from Microchip's portfolio of devices. One of their example projects that they provide is using that as an I3C target that can act as a GPIO expander. That's probably the closest device publicly available at this time.
Excellent. And there was another interesting one here about signal resilience from Arno. I know I3C is not specifically designed to be more resistant for immunity than I2C. Despite this, I was wondering if you think there is a significant difference between I2C and I3C with immunity performance. For example, the sensors are not always located on the same PCB assembly and can be connected with cables to other PCB assemblies and pick up unwanted noise.
On this one, I would say I3C has a better noise immunity because of the push-pull signal using also. Because the clock is always coming from controller to target, and this means that the controller could have a stronger drive on the clock line and making sure that the clock is pulled too high or low at the same time maintained. And by doing this, it can manage the clock noise on the clock line. When it comes to the data line, also by limiting the open drain communications to a few and very limited use cases, and all data transfers are communicated using a push-pull mode, we ensure that there is always signal integrity. But on top of this one, I3C also avoided the back and forth between controller and target by providing acknowledgement for every byte of data transferred. By saying this, what I mean is that in I3C, we have parity bit that is sent from controller for every 8 bit of data. There is a parity bit that is communicated to make sure that the data is protected by this parity and checked. And whenever there is a communication from targets, if you go to the DDR modes and the high data rate modes, we have a parity plus also the CRC protection for these communications, making sure that there is an extra layer of data integrity checking and also mutual verification of the data. In addition to this, there is also a list of provided and defined errors, error modes and errors that are defined, and a defined way of recovering from these issues whenever these parity errors or whenever there is a data communication conflict, because in open drain there is no way of knowing, but in push-pull communication, whenever there is a conflict on the SDA line or on the data line, devices could have an optional detection, and this error code is defined, and a pack-off feature is provided to ensure that the controller can easily recover the devices on the bus. So these are ways to make sure that it is resistant to noise and less prone to wiring or noise-related issues.
So you built in a degree of immunity. Thanks, AUL. I see we've gone over time by almost a minute now, so if you guys don't mind, I'll take a couple of questions from my audience, just general housekeeping questions. Will this session be recorded and the link shared for later viewing? Yes, if you're watching now, wherever you're watching, you'll be able to watch it later. So if you're on StreamYard, which you are, join with the same link and you can watch the presentation again. And then Milan wants to know if it is possible to get the presented documentation as a PDF file. Yes, it will be on the MIPI.org website within the next 48 hours. So just visit www.mipi.org and you can get the presentation there. So I'll take a final question, even though we are running a bit over. It's from Raul. I'm not a member of the MIPI Alliance. Can I still use I3C? What restrictions are there compared to being a MIPI Alliance member?
If we can answer, then during the presentation, I explained that there is an I3C member-only version with a vast set of features and an extended set of features, and we also have an I3C Basic that could be downloaded from MIPI website that is available in RAND-Z license, so it's free and reasonable, available for anyone who would like to use. It doesn't have the full set of features of I3C, but it includes the basic features of I3C and limited sets of features. Extra or additional optional features are also included on this. I believe that there is also a link to download this I3C Basic and I3C specifications that is included within the document or the presentation.
Awesome. So there's a lot more to learn. We've gone over an hour. I hate when that happens. It's a very interesting topic, and I want to learn a lot more about this, but I would suggest to our audience again, www.mipi.org. I'd like to learn a whole lot more, and with any luck, I might see you guys in Embedded World in March, and then I can catch up on your presentations and so on and so forth. But for now, 3 minutes over time, I'd like to thank our guests. Thank you, AUL Teferi. He's the chair of the MIPI I3C working group.
Thank you very much. Thank you everyone for joining. And please have a look at the MIPI website and I3C Basic also, and send us your feedbacks through the MIPI website.
Yeah. And Jonathan Giorgino, thank you for joining us. Jonathan's the co-vice chair of the MIPI I3C working group.
Thank you so much for hosting this.
And then, of course, Kai has an interesting title. He's evangelist and creator of the I3C Blaster. So thank you for evangelizing today, Kai.
Yeah, thanks for inviting me. It was exciting.
Great. It was very educational for me too. So I'll be looking forward to playing around a bit. And to our audience joining us from around the world, as always, thank you very much for joining us. Seems you guys enjoyed it. We got some great feedback here. Thank you. Very interesting presentation. Marek, great stuff, and so many other comments. So thank you, everyone from around the world, whether it's morning, evening, or afternoon there. Thanks for joining us, and have a good rest of the day.